We've never in our everyday experience seen an object that just keeps moving on and on and on forever without anyone acting on it. It seems like something will always stop. And this is why for most of human history, probably prehistory, but we definitely know the ancient Greeks all the way until the 1600s, all the way until the early 1600s, so for at least 2,000 years, the assumption was that objects have a natural tendency to stop. And these gentlemen show up in the 1600s, and you might be surprised to see three gentlemen pictured here, because this was about Newton's first law of motion. And indeed, one of these gentlemen is Sir Isaac Newton. That's Newton right over there. But these other two guys get at least as much credit for it, because they actually described really what Newton's first law describes, and they did it before Newton. This is Galilei, and this is Rene Descartes. These guys say objects have a tendency to maintain their motion forever, and the only way that you're going to stop them is if you act or accelerate them or change their velocity, so either their speed or direction some way, is to act on them with an unbalanced force.
Newton's first law is all about inertia. Basically an object's tendency to keep doing what it's doing. It's often stated as an object in motion will remain in motion and an object at rest will remain at rest unless acted upon by a force. Which is just another way of saying that to change the way something moves, to give it acceleration, you need a net force. Have two balls that are the same size, but one is an inflatable beach ball and the other is a bowling ball. The bowling ball is going to be harder to move and harder to stop once it's moving. It has more inertia because it has more mass. Makes sense, right? More mass means more stuff with a tendency to keep doing what it was doing before your force came along and interrupted it. And this idea connects nicely to Newton's second law. Net force is equal to mass times acceleration. Or, as an equation, F net equals ma. It's important to remember that we're talking about net force here, the amount of force left over once you've added together all the forces that might cancel each other out.
An object will accelerate in the direction of the resultant force. The bigger the force, the greater the acceleration. By doubling the size of the force, it doubles the acceleration. Also, a force acting on a large mass will accelerate it less than the same force acting on a smaller mass. By doubling the mass of the object, it halves its acceleration. The relationship between these variables can be shown by the equation F equals m times a, where F is the resultant force in newtons, m is the mass in kilograms, and a is the acceleration of the object in meters per second squared. For example, if a car has a mass of 700 kilograms and the driver pushes the car with an acceleration of 0.05 meters per second squared, then the force applied was 35 newtons. You can also use the formula to work out the acceleration and the mass.
Let's say you have a hockey puck sitting on a perfectly frictionless ice rink, and I know they're not usually perfectly frictionless, but stick with it. If you're pushing the puck along with a stick, that's a force on it that isn't being cancelled out by anything else, so the puck is experiencing acceleration. But when the puck is just sitting still, or even when it's sliding across the ice after you've pushed it, then all the forces are balanced out. That's what's known as equilibrium. An object that's in equilibrium can still be moving, like the sliding puck, but its velocity won't be changing. It's when the forces get unbalanced that you start to see the exciting stuff happen. And probably the most common case of a net force making something move is the gravitational force. Say you throw a 5-kilogram ball straight up in the air and then, get out of the way because that could really hurt if it hits you. But the force of gravity is pulling down on the ball, which is accelerating downward at a rate of 9.81 meters per second squared. So the net force is equal to ma, but the only force acting here is gravity. This means that if we could measure the acceleration of the ball, we'd be able to calculate the force of gravity. And we can measure the acceleration. It's 9.81 meters per second squared, the value we've been calling small g. So the force of gravity on the ball must be 5 kilograms, which is the mass of the ball, times small g, which comes to 49.05 kilograms times meters per second squared. We use this equation for gravity so much that it's often just written as Fg equals mg. That's how you determine the force of gravity, otherwise known as weight. Now,
whether crushing it or tapping it, getting the golf ball moving is explained by Newton's first and second laws of motion.
Newton's laws can be seen in all aspects of the game of golf, whether it's impact, whether it's the flight of the ball, or even the bounce and roll of the golf ball.
Newton's first law of motion, or the law of inertia, says that objects tend to resist change in motion. This means the motion of an object with balanced or zero net forces will remain constant. The force of Earth's gravity pulling down on a ball is balanced by the upward push of the tee. This balance of forces means there is a net or total force of zero, and the ball's state of motion remains the same. The force that a golf club applies to the ball is called unbalanced, because there isn't an equal force to push back, or balance the force of the club.
The rolling ball, it would be an example of a ball rolling on a line or a constant direction at a uniform velocity. It's going to stay at that uniform velocity unless it's affected by some external force.
Here, the external force is the friction of the grass. Newton's second law of motion relates to the motion of an object when an unbalanced force causes a change in velocity. How quickly or slowly the object's velocity changes is called acceleration.
Newton's second law really states or introduces the idea of acceleration. Acceleration of a body will be directly proportional to the force you apply to it, and it'll be inversely proportional to the mass of the object being accelerated.
This means that if a large force is applied to a small mass, it results in a larger or more rapid acceleration. If the same force is applied to a larger mass, it results in a smaller or slower acceleration. This is represented by the equation acceleration equals force divided by mass, more commonly stated as F equals m times a. Say the ball takes off at 176 miles per hour, or 78.7 meters per second. The collision happens in 500 microseconds. The change in velocity divided by collision time equals the acceleration on the ball. The mass of the ball is 1.62 ounces, or 0.0459 kilograms. The mass of the ball multiplied by the acceleration equals the force of the club on the ball. That's a force of more than 3/4 of a ton.
An object at rest will remain at rest unless acted upon by an unbalanced force. An object in motion continues in motion unless acted upon by an unbalanced force. Let's say you walking down the street cause you're going to the mall, and something knocked you off your feet cause you ran into a wall. So you were acted on by an unbalanced force, which means you ran into the wall and it threw you off course. Oh, I get it now. An object at rest will remain at rest unless acted on by an unbalanced force. Yeah, often called the law of inertia. Yep. Bradley, come tell him about the second law. Come on.
Force equals mass times acceleration. What? So I had to push a car to the gas station. It weighs 1,000 kilograms and rolls really slow. What? So it would take 50 newtons just for it to go. For real?
Oh, I get it. Acceleration is reduced when a force acts on a mass. The greater the mass of the object, the greater the amount of force needed to accelerate the object.